everyone, welcome to Insights by Rish. In today's video, I am going to explain you about confusion matrix and classification report in detail. Now, both confusion matrix and classification report are one of the evaluation metrics in classification models. It can be a binary classification model or it can be a multivariate classification model. But for this video, I am going to specifically focus on binary classification models. Now let us first try to understand what all contents I'm going to cover in this video. So I will explain about the confusion matrix, then some important elements and terminologies like true positive, true negative and all those. Then we'll try to understand how the accuracy, precision, recall and F1 score are computed, and we'll also try to understand what do we mean by support. Also I will try to show you the code so that by comparing the code and the theoretical part you can gain a better understanding. Now beginning with, your confusion matrix looks something like this. You have predicted values and you have actual values. Now on your x-axis you have predicted values and on your y-axis you have actual values. So wherever you have positive, you can have the value as a 1 or true or yes, and wherever you have negative, you can have the value as a 0, no or false. What this basically means is a TP stands for true positive, TN stands for true negative, FN stands for false negative and FP stands for false positive. Now take a look at the first grid. Here TP means true positive. What it is conveying that when you take the look at its y-axis, you have the value positive here, and when you take the look at its x-axis, you again have the value positive here. By this, what we mean is the actual label of the instance, or you can say the actual label of the data is positive, and the model is also predicting it to be positive, which means the model is correctly classifying it, because actually in the real the value is or the label is true, and the model is also saying it that the value or the label is true. So in this case, your model is correctly classifying your positive label. So this terminology is called as true positive, which means the positive points are correctly or truly getting classified. The second terminology, let's take the look at second terminology, which is false negative, FN. If you take the look at its x-axis, you will find the value negative here. And when you take the look at its y-axis, you will find the value positive here. By this, what I mean is, actually the value is positive, but your model is predicting it to be negative. Like it can happen that actually the person, if you are predicting it for any patient, and for like example brain tumor detection you are doing, and actually the person or the patient is having brain tumor, but your model is predicting it to be no. So this might be a dangerous case when it comes to the medical facilities. Like if the person is having any disease or any infection, but your model is predicting it that the person doesn't have anything, that's a hazardous cause. So false negative is a terminology where your actual labels are positive, but your model is predicting the values to be negative. That is, false negative means the negative points are falsely getting predicted. Like actually they are positive, but they are falsely getting predicted to negative. Now the next terminology that we have is a false positive, FP. Now again, when the word false precedes, you can understand that there is some misclassification. When you take the look at its x-axis, you have the value positive, and when you take the look at its y-axis, you have the value negative. False positive means actually the label is negative, but your model is predicting it to be positive. Like in case if the person doesn't have brain tumor, but your model is predicting that the person has. Now this is not that hazardous as compared to false negative, because if the person doesn't have anything, no matter what misclassifications your model does, but still that won't cause any deterioration in the person's health. So false positive basically means the actual value is negative, but the model is falsely or wrongly classifying the value to be positive. That is false positive. And the last terminology is true negative. By true negative, what I mean is actually the label is negative and the model also predicts it to be negative. So whenever the word true precedes, you can understand the classifications are done rightly, and whenever the word false precedes, you can understand that there are some misclassifications. So true positive means actually the labels are positive and model also predicts it to be positive, while true negative means actually the labels are negative and model also predicts it to be negative. Now let us try to understand this by an example. So before understanding this example, let me show you this code first. I have created this demo data where we have name, experience and job. This is the very basic classification model where your input will be experience and your target will be job. Depending upon your experience, the classification model will decide whether the person will get the job or not. 0 means person won't get any job and 1 means the person will get job. That is, 1 is your positive class and 0 is your negative class. Now let us start coding for that. First, we will import all the necessary libraries that we require. So we'll say import pandas as PD. Then we also require matplotlib dot pyplot as plt. Then we require cbun. And we also require warnings so that the Jupyter Lab doesn't give us any warnings. And ignore. Now we will use the basic logistic regression here. You can go ahead with any classification algorithm you want to, but as this is just for an example, a simple basic example, I will go ahead with logistic regression. So I will say from sklearn dot linear model, I will import logistic regression, and for evaluation we'll say from sklearn dot metrics, we will import the accuracy score, the confusion matrix, which is the main topic of our video, and the classification report. So these are all the libraries that we required. Next, we'll start by importing the dataset. So we'll say we'll import the dataset into a variable df. We'll say pd.readcsv. This is the path on which my dataset is stored. Let's run that, and let us try to display the dataset. So this dataset consists of 15 rows starting from 0 to 14, and we don't require the column name because that's categorical and that won't help us into our predictions. We require the column experience, which will be our input, and job, which will be our output. So we will start training our model directly. What this dataset basically means is you have input, you're going to input the experience the person or the employee has, and you want to predict whether the person will get job or not. For example, in the first instance, the experience is of 5 years, so that the person will get the job. Again, in the second instance for Jonathan, the experience is of 7 years and the person will get job. The value is 1. But for the James, for instance 2, the experience James has is only of 1 year, and hence he won't get any job. So this is what you do, and wherever you encounter the experience 0, which means the person is fresher. Now starting with, we have already imported the libraries. We'll directly go ahead with building our model. So we'll say model is equal to logistic regression, and we will fit our model. Now, as this is a very small data set, we aren't going to divide it into the training, testing and validation set. We'll directly supply the experience here and the job. So our X-tray, that is our input, is experience. And the target feature that we have is job. Let's run this. And the error says expected 2D array. So we require a 2D array here for input. Now our model has been trained on the logistic regression. We will try to make some predictions. So we'll say model.predict. As we don't have any testing set here, we will provide the experience column itself to the prediction as well. So we will say df predict for the experience. Again, we require 2 columns here. These are our predictions, and we will store all these values in a variable called pred. Let's run that. And now we want to compute the accuracy. So what we'll say accuracy score, and here you want to supply the first true labels. So your true labels are stored in your job, and your predicted labels are stored in pred. And we'll multiply it by 100 as we want our accuracy to be displayed in percentage. As you can see, the accuracy of this model is of 86%. Now, though we have supplied all the data and we are again predicting our model onto the same data that we have supplied, still we aren't getting 100% accuracy and just 86% accuracy. This is because we don't have any generalized patterns here. We don't have any specific patterns here. The values are randomly placed here. Now, this is our accuracy score. But the main motto of this video is computing the confusion matrix. We'll start with that. We'll say CF, which is the confusion matrix variable into which we will build our confusion matrix. So we'll say confusion matrix. And we have to provide the true label here, which is your job, and the predicted values, which are stored in pred variable. Next, you want to plot a heat map in order to visualize your confusion matrix. So you are going to use the Cbun library that you have already imported with the alias SNS, and you will say SNS.heatmap. Here you will provide your variable CF. Then you will say A0 is equal to true, as you want the values to be displayed on the grid, and the color of your confusion matrix. You can set any theme. I will set it to be crest. Let's run this, and this is your confusion matrix. Let us also label that for better understanding. So for labeling, we will use matplotlib here. So we will say plt.xlabel. On x-axis, we have predicted values, so predictions, and on y-axis, you have actual values. So actual. Let's run that. And this is our confusion matrix. As you can see, here you have predictions on your x-axis, and on your y-axis you have actual values. Now we will understand whatever theory we studied. We'll try to implement it here. So what this confusion matrix is inferring to is 6 times, like total instances are 15. We have total 15 rows into this particular data set, and this confusion matrix is saying that out of 15 times, 6 times it's happening that the original label is 0, that is the person won't get the job, and the model is also predicting the same. That is, you have the 0 0 coordinate. You have 0 on your actual, that is on your y-axis, as well as you have 0 on your x-axis for predictions. So it's saying that out of your 15 instances, 6 times it's happening that actually the person isn't getting any job, and the model is also predicting the same. While only 1% it's happening that the person isn't getting any job, but your model is predicting it to be that the person is getting the job. That is, on your y-axis you have the label 0, that is the actual label, and on your y-axis you are having the label 1 for the predicted. So originally only one time it's happening that actually the person isn't getting any job, but your model is predicting that he is getting. And again, only for one time it's happening that the original true label is 1, that is the person is getting the job, but your model is predicting it to be 0, that is the person isn't getting any job. And 7 times, that is out of 15 instances, 7 times it's happening that the actual label is 1, that is the person is getting job in real, and your model is also predicting it to be same. This is what our confusion matrix tells us. Now going back to so this is what our confusion matrix tells us. Now we'll also try to plot the classification report. So we'll say print classification report. The classification report is based on the confusion matrix. Whatever computation you are performing in your classification report are based on your confusion matrix. So confusion matrix lies as a base foundation of evaluation metric. So again, you want to pass the same things here, the true labels which are stored in job, and your predicted labels which are stored in pred variable. Let's run that, and this is your classification report. Now we'll try to understand what this every individual terminology mean. So you have 4 individual terminologies here: precision, recall, F1-Score, and support. Let us try to understand what they mean. And you have this terminologies for every individual class. Now, as this is a binary classification problem, you are having the precision, recall, F1-Score, and support. For class 0, you have different values, and for class 1 you have different values. If you are doing any multivariate classifications, like if you're predicting handwritten digits of MINS dataset, in that case you have 10 inputs or 10 classes from 0 to 9. In that case you will get these values of precision, recall, F1-Score, and support differently for every category, for every class. Now going back to the presentation, accuracy, how the accuracy is calculated. Now I already told you what the true positive, true negative means. Now in accuracy, on the numerator you have all the true values, that is true positive plus true negative, and divided by you have all the values then, true positive, true negative, and false negative. So I have used the same example that I have implemented right now in the code here. The same image I have fitted here. So what this means is, On the numerator, you have all the true values, that is your true positive, that is the positive points which are correctly getting classified, and true negative, which means all the negative points that are correctly getting classified. So true positive value of your true positive is 7. True positive, here your class 1 is your positive class, as it's giving a positive meaning that a person is getting a job, while the class 0 is your negative class, which means a person isn't getting any job. So here your true positive value, that is the actual is 1 and the predicted is also 1, the value is 7. So your true positive label is 7. True positive label is 7. And then for true negative, that is actually it's negative and model is also predicting it to be negative, that is 0 0. So actually 0 and predicted also 0. So you have the value 6 here for true negative. So true positive is 7 and true negative is 6, divided upon everything that you have, all your true positive, false positive, true negative and false negative. And when you compute, you get an accuracy of 0.8666. So when you approximate it, you get an accuracy of 87%. And if you check the classification report here, you will find that the accuracy here is of 87%. Or even if you calculated here that using the accuracy score, you got an accuracy of 86.66%. So this is what we computed right now. We computed this accuracy. So this is how your accuracy is computed. The next terminology that you have here is precision. Now accuracy is computed for all the categories that you have in general. You don't have accuracy calculated for every individual class, that is for class 0, for class 1, no. Accuracy is in general for entire data set that you have, no matter how many categories it consists of. While the precision, recall, all other parameters are computed for individual categories. Like you will have a value of precision different for your positive class and the value of precision different for your negative class. So here, firstly, we are computing the precision for class 1, that is for the positive class. So as you are computing the precision for the positive class, on the numerator you will have true positive, and divided by you will have true positive plus false positive. Basically, whenever you are calculating the precision for any positive class, you consist of all the positive values in your numerator as well as in your denominator. It doesn't matter whether they are true or false, but all the positive values. So on your numerator you have true positive divided by true positive plus false positive. Now your true positive is 7, that is actual label is 1 and the predicted also is 1. And your false positive, that is your actually it's negative, but model is predicting it to be positive. This is 1. So on a denominator you will have 7 plus 1. And the precision for positive class you will get of around 0.875, and when you approximate it, you will get a precision of 88% for the positive class. And when you take the look at your classification report, you will find that you are getting the precision of 88% for your class 1, that is for your positive class. This is what we are computing. And now the precision will be different for negative class depending upon its values. So precision for negative class will be something like this. There for the positive class we had all the positive values. Here, while calculating the precision for negative class, we will have all the negative values. That is true negative divided by true negative plus false negative. So your true negative value, that is the original value is negative and the model is also predicting it to be negative. Your value is 6 for that. So your numerator would be 6 divided by true negative plus false negative. False negative means originally the point is positive, but your model is predicting it to be negative. So this one. So on the denominator you will have 6 plus 1. And for precision for your negative class, you are getting it again 0.857, and when you approximate it, it will be 0.86%. So when you check the precision for your negative class, it is 0.86, that is 86%. And that's how precisions are computed. The next individual terminology that we have is recall. So the formula for recall is recall for positive class, and again you will have recall value of positive class are different and value of recall for the negative class different. So recall for positive class, the formula is true positive upon true positive plus false negative. So on your numerator you will have true positive as you are computing your recall for positive class, and on your denominator you will have true positive plus false negative. So your true positive value is 7 and on the denominator you will have true positive, that is 7, plus false negative, that is originally the point is 1, that is the point is positive, but your model is wrongly classifying it to be negative, so that is 1. So on the denominator you will have 7 plus 1, and when you compute you will get the value as 0.875, and when you approximate it you will get 0.88. So when you check the classification report, you will find that the recall for class 1 is of 88%, and then the recall for negative class. So the formula is true negative upon true negative plus false positive. On your numerator, you will have true negative as you are computing the recall for negative class, and on your denominator, you will have true negative plus false positive. So your true negative value is a 6, and divided by 6 plus your false positive, that is originally the point is negative, but your model is predicting it to be positive, so this one. So on the denominator you will have 6 plus 1. So when you compute that, you will get the value as 0.857, and when you approximate it you will get the value 0.86. So when you take the look at your classification report for the negative class, you will find that the recall for negative class is 0.86. So this is how the recall is computed. Now in this case, you will find that the precision, recall, F1-Score, all these values are same for respective categories. But it's not the case in every model. This is because we just had a limited data set and a very simple algorithm. We didn't did anything extra. We just built a basic model, and that's why we had a precision, recall, and F1-Score same for every respective category. But in real time models you will have every value will be a different value. Now the second last terminology that we have here is F1-Score. Let us try to understand how the F1-Score is computed. Now for F1-Score, what you do is, now here you are computing your F1-Score for negative class, that is 0. So what you will do, you will multiply the whole thing by 2, and on your numerator you will have the precision for 0 class into your recall for 0 class divided by precision for 0 class plus recall for 0 class. So numerator and denominator is almost same, the difference is only of sign. On the numerator you have multiplication, on the denominator you have addition. So the precision for class 0, when you so the precision for class 0 is 0.86 and 0.86, and the recall for class 0 is also 0.86. On the numerator you would perform multiplication, on the denominator you will perform addition, and when you compute the value you will get the value as 0.86. So your F1-Score for your negative class, that is for class 0, is 0.86. In a similar manner you want to compute a F1-Score for positive class, that is for class 1. Everything remains same, just you want to consider the values of positive class. So on the numerator you will have precision of class 1 multiplied by recall of class 1, and on the denominator you will again have the same terminologies, but on the numerator you will perform multiplication, on the denominator you will perform addition, and everything else remains same. And when you compute you will get the value 0.88. So your F1-Score for your positive class, that is for class 1, is 88%. That's how you compute your F1-Score. And the last individual terminology that we have here is support. Now support doesn't have any such formulas like we had in F1-Score, recall, and precision. But support, it basically says that support refers to the number of actual occurrences of each class in the dataset. It means that how many rows in your entire dataset has that particular label. You just want a count of rows wherever you have that particular label. Like for example, here your support for class 0 is 7, which means in your entire data set of 15 rows, you have 7 rows where your class label is 0. And if you calculate, you can see that 1, this 1, then 2, 3, 4, 5, 6 and 7. You have 7 instances or 7 rows where you have the class label as 0. And support is 8 for 1, which means you have 8 such instances in your data set where the class label is 8. So 1, 2, 3, 4, 5, 6, 7, 8. So out of 15 instances, on your 7 instances you have class label 0, and on your 8 instances you have class label 1. Support basically tells us that how many instances falls into that particular respective category. So this is how you compute your confusion matrix and classification report, and this is how you can interpret the results out of that. So that's it for the video. Thanks for watching.